Okay, so we're looking at section 8.3, and in section 8.3 we learned some tests we could use to establish convergence or divergence of a series with positive terms. And I have a question that I want to ask. So this is the example I wanted to do, okay, for section 8.3. It's yet just another example. So the previous one that I just did tonight, delete that. This is the example I meant. Is the series given by 1 over the square root of m cubed plus 1, is that series convergent? Okay, and we're going to use the comparison test. So you have the comparison test, the limit comparison test, and the integral test. Generally, I try to use the comparison test first. At least I consider it first. Now, sometimes it won't work well, okay, depending on your series. But this series will work, because 1 over the square root of n cubed plus 1 is less than or equal to 1 over the square root of n cubed, which is equal to 1 over n cubed to the half power, which is 1 over n to the 3 halves. Now, why am I interested in this series? What do we know about the series n equals 1 to infinity of 1 over n to the 3 halves? Good, Leping, that's a p-series. That's a p-series. What is your p equal to? Right. This is a p-series. Good, Renan. With p equals 3 halves, which is greater than 1. So is this p-series a convergent p-series or a divergent p-series? It's convergent. A p-series is any series, okay, of this form. Now, we usually put n equals 1, but it could start at n equals 1,000,000. The starting value, the starting index, doesn't matter for convergence or divergence of a series. What matters is how the series behaves as you move out to infinity. What's the end behavior, so to speak, of the series, or the eventual behavior? Let's put it that way. So p-series is any series that takes this form here, any series that takes this form. And the series given as 1 over n to the 3 halves power, that series converges, because when the p is greater than 1, we have a convergent p-series. When the p is less than or equal to 1, we have a divergent p-series. So normally when we use the comparison test, it's most convenient if we can compare our series to some kind of p-series. All right, well now, what can we say? What can we say about our series? Here's our series. how does R series relate to the P series? It's less than. Good. Good looking. So here's our series. Okay, there's our series. And I'll try to write it nicely. I'm kind of restricted to one page here, so I'm trying to fit it in, but still be good. Okay, and equals. Okay, and here is our P series. Okay, with P equaling 3/2. Try to write that in. Right? I mean, does this statement here make sense? That R series, the sum of R series, would be less than the sum of this convergent P series. Does that make sense? Okay, Tal's comfortable with that. Well, since that's true, R series also converges. Okay, R series here, R series also converges. And that's how you can use a P series to help you. So on the right here, I know it's tight, but I wrote R series also converges. Okay. Are there any questions on that? All right. Well, I'll go ahead then and go back to. I actually want to bring up an ebook example here. Just give me one moment. One moment, class. Just bring it up here. Waiting for the ebook to come up. If it, hold on here. I'm gonna have to log out and come back in a WebAssign. Let me try it here. One moment, class. I want to bring up I want to do another example from section 8.3. We've looked at a lot of examples, and here was yet another one. But and when you work on your section 8.3 assignment, there are you know, in the beginning there they have those like very guided exercises that break things up into parts. Okay, so let's get this ebook open. All right, well, ebook's given me a little, it's just taking a little time. I don't know why. But at any rate, let me go ahead and bring up the other example here. Okay. Let me give you a moment to copy this example down, okay? What kind of series is this, by the way? What kind of series is this?
Harmonic.
A harmonic series would be a P series, but what's P equal to for a harmonic series? Here's the harmonic series.
1.
That's right. So harmonic series diverges. Notice that P is equal to 1. So this is, well, I guess I kind of gave it away. What kind of series is this where you have 1 over n to the 4th? It's a P series. That's right, Sophie. And what's P equal to? 4. That's right, Leping. So does this series converge? That's right, Sophie. Does this series converge? It does. This series here converges. And because of that, the sum is finite. It reaches a limit. So it would make sense to say, hey, let's estimate the series correct to 2 decimal places. It would make sense to ask that. All right, so let me give you a moment to copy the example. Okay, and what I need in the problem, I have actually on the solution. We're going to use what's called the remainder estimate for the integral test. And I actually have that stated. Since I'm having a little difficulty bringing up the ebook right now, I can tell you the remainder estimate for the integral test is it comes before example 6 in your book. And I actually displayed that remainder estimate for the integral test. I actually displayed that in the last class. Like I showed you that in class, the theorem. But let's go ahead and look at it. I have it written down. Okay, and remember, use a zoom on the right if you need to blow your screen up. This is the remainder estimate right here for the integral test. So what does R sub n mean? It's the remainder. So if we're going to approximate a infinite sum, which we denote by the series, or we denote that also by S. When you see S, that means you're talking about the infinite series. If you're going to estimate the sum of the infinite series by adding up the first n terms of the series, you're going to have an error, right? You're going to have an approximation. Well, the error in the approximation is denoted by R sub n. And what's important is that the error in your approximation, the remainder, is going to be less than or equal to this integral here, this improper integral. So for instance, for our series, n equals 1 to infinity of 1 over n to the fourth, for our series, the remainder is bounded by the integral from n to infinity of 1 over x to the fourth dx. Okay, so we have to figure out how many terms do we need to add of the series so that our estimate is correct to 2 decimal places. The way I'm going to determine that is by using the remainder estimate for the integral test. The remainder for our estimate, the error in our estimate, will be less than or equal to this integral on the right. Okay. So notice that in terms of sort of the notation here, this 1 over n to the fourth is f of n, and 1 over x to the fourth is f of x. Okay, so sometimes it's helpful to keep that in your mind. So, okay, well, now one thing I'll mention here, this is just a side note, but you use the integral test only when the integral test applies. Now, the fact is that this function, 1 over x to the fourth, is continuous, positive, and decreasing over the interval 1 to infinity. And therefore, we can use the integral test. So now we can use the remainder estimate for the integral test. So let's go ahead and figure out this improper integral. So you've had section 5.10 before. Okay, you demonstrated that on the last exam, your knowledge of that. I'm just going to write the integral as the limit as t approaches infinity. So I replace the infinity with t. And then I go ahead, the antiderivative of x to the negative fourth is negative x to the negative third over 3, or x to the negative third over 3. I'm going to substitute in t and n, and then take the limit. By the way, the negative 1/3 I can bring out in front of the limit. What happens to 1 over t cubed as t gets large? What does this go to?
0.
It goes to 0. And so you're left with negative 1/3. That's right, Samuel, good. You're left with negative 1/3 times negative 1 over n cubed. That's 1 over 3n squared. So in other words, the remainder of our estimate will be less than or equal to 1 over 3n cubed. Now we want our estimate to be correct to 2 decimal places. That means we have to set our bound here, the 1 over 3n cubed, to be less than or equal to 5 over 10 cubed. Okay, so if we were to say why 5 over 10 cubed, it has to do with ensuring that your estimate's correct to 2 decimal places. If we wanted our estimate correct to 3 decimal places, we will want our upper bound less than or equal to 5 over 10 to what power?
If we want how many decimal places?
If we wanted, okay, so one thing I'll mention here This might make this a little more intuitive. 5 over 10 cubed is 0.005. Okay, that's 5 over 10 cubed. So if our I want to say this the right way, if the difference between the true sum and the nth partial sum is less than 0.005, we're ensured that our estimate, our partial sum, S sub n, will be correct to 2 decimal places. Now, what if we wanted our estimate to be correct to 3 decimal places? We wouldn't use 5 over, and note, by the way, correct to 2 decimal places. Notice that the 3, the 10 cubed on the bottom, the 3 there is 1 more than 2. So if we wanted our partial sum, our estimate to be correct to 3 decimal places, we would use 5 over 10 to what power? That's right, Nathan, 5 over 10 to the 4th. That's right. If we wanted the estimate to be correct to 6 decimal places, we would want the remainder, the R sub n, to be less than or equal to 5 over what? 10 to what power? If we want it to be correct to 6 decimal places.
10 to the 5th.
I'm sorry, Samuel?
10 to the 5th.
Well, if it's 6
decimal places? Oh, no, 10 to the 7th.
10 to the 7th, that's right. So that's the general rule. Okay, the reason, Renaud, that we don't, so Renaud's saying, okay, well, why have a 5 up here? Why have a 5 up here? Why not have a 1? It has to do with rounding. It has to do with rounding. Don't you use like if it's more than you know, when you round, doesn't it matter whether the number whether the decimal place is higher than a 5 or lower than a 5 as to what you're going to round to? Yeah, that's why you have the 5 there. That's why you have the 5 there. Good question. Good question. So we want our 1 over 3n cubed to be less than or equal to 5 over 10 cubed. Okay. In other words, we know that our error in estimating the series with the nth partial sum, our error, R sub n, is less than or equal to 1 over 3n cubed, and that's less than or equal to 5. We're going to set that less than or equal to 5 over 10 cubed. So this will ensure that our estimate is correct to 2 decimal places. So now we just are going to solve this inequality. We're going to solve this inequality. Let me ask one thing here before. Let me go to the whiteboard, and I'll come back to this. Hold on. One moment here. So at that one step there, we had 1 over 3n cubed was less than or equal to 5 over 10 cubed. Okay, and what I'm going to do is I'm going to multiply both sides by 3n cubed. Both sides of the inequality I multiply by 3n cubed. So then on the left side, I'm going to get 1. On the right side, I'm going to get 15n cubed over 10 cubed. And the inequality doesn't change. Now, I thought with inequalities, sometimes the sign switches from a less than or equal to a greater than or equal, and vice versa. But we don't need to worry about that here. Why don't we need to worry about that here? Why does the inequality stay less than or equal to based on what we're multiplying here? You know, we're multiplying both sides of the inequality by 3n cubed. It doesn't change the sign of the inequality. Why is that, Samuel?
Because there is no negative in the equation.
That's exactly right, and Nathan agrees. And n is a positive integer. So this, in fact, is true. And, you know, of course, what we want to do here is isolate the n cubed. So what would I multiply both sides of this inequality by to get the n cubed by itself? If I want to
10
get on the
cubed over 15.
That's right, 10 cubed over 15. Okay, so now 10 cubed is 1,000. And so we're going to get n cubed is greater than or equal to 1,015ths. Are there any questions on that? Let's see, hold on here. One moment, there's a question. Let me see, Marcus, hold on. Okay. Okay, Marcus, that's fine. That's fine, no problem. All right, let's go ahead then. Are there any questions on this? Okay, well then let's head back to the solution here. Okay, so we're down here now. We're down here. And I'll go ahead and move to the next page. We want to solve this inequality for n. So, okay, n cubed is greater than or equal to 1,015ths. We'll take the cube root of both sides. Okay, so in other words, what I'm doing here, if I put in a little more detail, is I'm raising both sides of the inequality by 1/3. And it doesn't change the inequality sign at all. 1,015ths to the 1/3 power is the cube root of 1,015ths. And so n is going to equal 4.0548. But that means then we're going to need 5 terms. 4 terms is not enough. The number of terms is an integer. 4 terms is not enough because n has to be greater than or equal to 4.0548. So we need 5 terms. Are there any questions on solving the inequality? All right, well, let me just show you now what this would mean. Okay, so what I did here was I added the first 5 terms of this P series. So the P series is approximately, right, that's approximately equal to 1/1, well, it equals the sum of these first 5 terms. And if you add them together, okay, and I guess I went out to, let's see, tenths, hundreds, thousands. Let me see, hold on. I went out to the billionths place. That 9 there is in the billionths place. Okay, so that should be correct to do to 2 decimal places. Now, what I did was I said, okay, that's the 5th partial sum. Let's look at the 6th partial sum, and you'll see that the 6th partial sum, that would be if I added then another term, 1 over 6 to the 4th. If I added that, then this would be my 6th partial sum. And if you look at the 6th partial sum and the 5th partial sum, you see how you got, after the decimal point, the 0.08, 0.08. You see that? So they agreed to 2 decimal places. So therefore, we say our estimate is correct. If we have the 5th partial sum for this series, that estimate is approximate the series correct to 2 decimal places, because adding more terms of the series doesn't change the first 2. It doesn't change the first 2 decimal places. The 0.08. Samuel, question?
Why do we need 5 decimal places? I mean, 5 terms?
Well, when we solve for n, you agree the inequality gave us that n is greater than or equal to 4.0548.
Yes.
Right? So n is the number of terms you're going to add, right? N is the number of terms. N is the number of terms to add. Can I add 4.0548 terms?
No.
No. Has to be an integer. Well, is 4? Could I round down and use 4 terms? Would that be okay?
I guess not.
And it's because algebraically you need 4.0548. N has to be that large. So therefore, practically speaking, you need 5 terms. You see, you always round up. You put it that way, you round up. Does that make sense, Samuel?
Yes, thank you.
Okay, excellent. All right, good question. So therefore, our series is approximately equal to 1.08, which is correct to 2 decimal places. And you know, if you're doing computations and you know that's good enough for you, then use that estimate. But a lot of times, right, you're going to want a lot more accuracy. Well, how are you going to get more accuracy in your estimate? Okay, what if, for instance, you wanted an estimate, which would be a partial sum. What if you wanted a partial sum correct to 5 decimal places? What would you need to do?
Add on the 6th term.
Well, would the 6th term be enough? But Samuel, you're right in the sense you're saying we would need to add more terms, right? And you're right. How many terms do we need to add? Oh, well, what we would do is we would solve this inequality. It's just if we wanted correct to 5 decimal places, on the right-hand side, instead of 5 over 10 cubed, we would have 5 over 10 to what power? If we wanted our estimate correct to 5 decimal places, we would have
6.
5. That's right. That's right. So you see, you can program a computer. How many are computer science majors in here? I know we have some. Okay, Jazi is. Samuel is. Okay. So, you know, you could program a computer to, you know, solve the inequality and then automatically add a certain number of terms. And you might think, well, what's it matter? You know, computer can add a lot of terms very quickly. It does matter because you might need to add like, you know, 1 trillion terms to get the accuracy you need. And maybe it would take a long time for the computer to do that. But maybe you don't need to add 1 trillion terms. Maybe you only need to add 1 billion terms. You see, there's a difference, right, in computational time. And when I was your age, well, younger, a teenager, you know, computing power wasn't as good as it is now. So, you know, these kind of questions make a difference. But even now, these kind of, you know, knowing how many terms you need to get the accuracy you want is really very important. But on that note, are there any questions? Any questions? Any questions here on this example? And this is the last example for section 8.3 that we'll do. Yes, Samuel.
I noticed I don't believe that we used any examples for regular integral test.
Well, we had one we looked at one in the recording in our last lecture, but I'll tell you, you're going to do an example when you work on the section 8.3 homework. You know, like in the beginning, those examples that like break down the details. You're going to have one of those, so you'll be able to work through one. I agree. I want you to work through one. So that's a good question. Okay, well, let me go ahead and stop the recording here.